Hello, I'm Professor Steve Miller. Welcome back to Compressible Flow. Today we're going to be talking about a few particular subjects as part of our introduction to the class. The first, of course, is flow regimes and their definitions, which we'll divide by Mach's number, the Mach number. Then we'll look at compressibility and define it mathematically. We'll also remind you about some of the notations which you should have known from your aerodynamics or fluid dynamics classes which you've taken previously. Then we'll go in and define, of course, Mach number and talk about Mach number effects on devices. It's always fun to start with a quote. Here's another one from Da Vinci, as I showed earlier. He wrote in one of his notebooks, "Before writing on winged creatures, make a book on incident objects that descend through the air without wind." In other words, the laws of gravity and falling bodies. And another on those that descend with the wind, in other words, the laws of air resistance and aerodynamics. Da Vinci was, of course, a genius, and he saw then that he would try and so-called divide and conquer a problem to study its elements and assemble it into something more complicated. This is very much like what we're doing in this class, that we're looking at elements of very complicated flows and to understand them as a system of fluid dynamics. So let's start at the beginning, and this is a little bit of a review for some of you, and that's okay, but I'm trying to bring everybody to the same page. We first might ask, what is a fluid? Well, a fluid in this class, and most people would agree, is any substance that deforms continually under a shear stress. So we take any substance and shear it, and it will continually deform. This is what we call and consider a fluid. Generally, there's three states of matter, which, in the classical sense at least, that we consider a fluid. Those which would be liquids, like water, gases, such as, say, nitrogen gas or air, and plasmas, which is just perhaps a gas which is heated enough for the state of matter to form and for the gas to disassociate. In this class, we'll mostly look at gases. We will not be looking at plasma dynamics. We very seldomly will look at liquids because the compressibility of liquids is so small. The compressibility of gases and plasmas is very, very high. So compressibility effects in gases and plasmas are high, and therefore we're going to focus on them a little bit more. Now, most liquids will show almost no change in density or changing in pressure. We note this from experiments, and we'll see why momentarily. For this reason, we consider, at least in engineering contexts, liquids to be considered rather incompressible for practical purposes. For example, if we're doing calculations, we might just assume that the density is not varying within the flow field. And we would call this, in a casual manner, it's not the strictest definition of compressibility, which we'll talk about later, that the flow would be incompressible. And that's a wonderful assumption because we can reduce the number of equations we're solving for, and thus reducing the complexity of the problem. Compressible flow needs a greater insight into the problem because density varies in the flow, and we have to account for that as an unknown variable. So you see here, I'm already introducing some variables which you might make notes on because we'll be using them mostly concisely through the class. And these are chosen by the fluid dynamics community, which has been in existence for hundreds of years. So I suggest that you start getting familiar with the variables we're using here. Rho, where my cursor is, of course, is the density, and it changes with pressure, P. This is the static pressure, P, and the static density, rho. Now, unlike liquids, gases readily change with pressure, P. This is something we're observing from experiment. If we can model a gas with the so-called ideal gas law, which I show in equation 1, and all equations are numbered in this class, we can write it as P equals rho RT. Then we can also use this gas law for many other fluids. But you have to know when it breaks down. Remember, the gas law is for ideal gases, and it is a type of assumption. So we'll look at some of the validation and ranges where these different gas laws work well in this class. So here we say the ideal gas law, which I think almost everybody's seen at some point in their career up to this point. If not, here it is. I think it's usually introduced in chemistry, is P, the static pressure, equals rho, the static density, times R, the gas constant, times capital T, which we'll call static temperature. And I'll talk about static total and stagnation values later. Just know that P is pressure, rho is density, R is gas constant, and T is temperature. P equals rho RT. It's an equation that you should remember. And all the important equations in this class I've put on a formula sheet, which is available on the class website. And I'll discuss those later, probably in class itself or online. And it's also posted on the class website. Now we note an informal definition of an incompressible flow is one where the flow density changes spatially and or temporally. We will call these compressible flows. That's one where the density is changing as we move around in space or time. That is a compressible flow, and the one we'll use for this class. It's not the strictest definition, which of course comes out of Euclidean geometry and mechanics and the formations of the equations of motion. And we'll talk about that briefly later, but it's not essential for the class. Let's talk about what compressibility is. For now, we'll call compressibility and quantify it as tau. So tau, the Greek letter here, will be defined as compressibility. Don't think of tau too closely as compressibility in the rest of the class. It's just the formal definition here. We'll call tau as compressibility. We'll also use tau as shear stress, which we'll also show in this introduction module. So you'll know tau as shear stress or compressibility by the context of the problem and the equation that's used. Why do we use the same variable for two different things? Tradition. And it's because these two communities that just studied the fundamentals of gases and fluid mechanics and dynamics came together, and they both were using tau. Neither one gave way. So we'll use tau twice in this class for the same thing. It should be obvious to you which it is. Let's now let tau be equal as 1 over v times dv dp. You can see I've already defined P as the pressure, and tau is compressibility, but V will be the volume. So the compressibility of a fluid will go as the negative of 1 divided by the volume, the initial volume, times the change in volume divided by a differential change in pressure. So if we apply a little positive pressure, get a little positive differential, what happens to the volume? Change in volume dV, so it's dV dP. That's just a normal derivative. In this class, we'll see normal and partial derivatives. You should understand already what a derivative is from your calculus sequences, and I'm sure that they briefly talked about a partial derivative. And we'll briefly review that if you don't recall this. So we will also use V as a component of velocity in the class, so be ready for this. Now this is shown down in a control volume, and it could be one where there's flow. This is an Eulerian framework. Here we have a coordinate system of x, y, and z, and it's a right-handed coordinate system, so if we do the right-hand rule from x to y, we get the z direction out of the page. We have a control volume, which you should be familiar from your previous classes. It's like this strange potato-like shape in figure 30. Now, this, of course, is not a solid wall. It's just a mathematical surface which we place through the flow field. And the flow field, remind you, is where we have, say, densities, pressures, velocities, temperatures going through some space and time. We've drawn some streamlines, and so flow is coming in from the left side of the control volume and going from the right. It doesn't really matter. There could be no flow or flow. Right now it's arbitrary. It's just a coordinate system. On the surface of this control volume, we have some small differential element ds. We have B, which is this little location of it, and we have a normal vector, and this normal vector is always outward pointing in our class on the control volume. And there's some velocity vector, which we'll call capital V for now, located on the control volume surface. So this is our general control volume and our definition of tau. And through your homework, you'll try and calculate one particular compressibility. Now there's a few interesting points that must be made about the compressibility itself. We have the so-called isothermal compressibility, and if you remember back to your thermodynamics classes, you'll have learned these words like isothermal, adiabatic, and isentropic. If you don't remember them now, now's a good time to go back and review, because you're expected to know these things. Isothermal compressibility is the compressibility occurring in equation 2 in this case while temperature is held constant. Of course, if we compress gases, say we take that volume and make it smaller, you wouldn't expect temperature to necessarily remain constant. This is artificial in some sense. So we're holding temperature constant. It's an assumption of the process, and it could happen in certain physical cases. Now, there's also isentropic compressibility. That's when there's constant entropy, and we haven't defined entropy yet, but I think you know from your second law of thermodynamics that entropy should increase in the system. That is, the disorder in the system is increasing. We'll talk about entropy and define it later in the introduction module, so you can remember if you forgot. Now, compressibility, as you can see, is a property of the particular fluid, which we define mathematically. If we take water and air and perform our little test, we take a control volume and make it slightly bigger, say by changing dV. We can observe how pressure changes and divide by the volume, of course. Multiply -1, we get the tau, compressibility, in units of meter squared per Newton at an initial pressure of 1 atmosphere. So ATM is atmosphere, N is newtons, M is meters, and that's squared. So these are the units. Now, if we do that for water, we'll get a compressibility of 5 times 10 to the -5. That's rather small. If we do it for air, you'll find we have a compressibility of 10 to the -5, and the units are the same. So if we take water and air is 5 orders of magnitude, approximately, more compressible than water. And you can see this. It's very hard to compress water. Like if you put it in a box and try and compress it, it takes much, much more force than, say, water would, or excuse me, air. We can also take equation 2 and write it as and in terms of density. We can also take equation 2 and write it in terms of density. That'll be tau as 1 over rho of d rho dp. You can try and exchange these two values yourself. This is a little bit easier to work with, but we have a differential form. What if we try and move d rho to one side and dp to the other? We'll find this nice differential equation. Let's say d rho equals rho tau dp. Recall that d are the differentials, rho is density, p is pressure, tau is compressibility here. We get d rho equals rho tau dp, equation 4. So if you don't see these mathematical steps, please look back at your calculus book and of course your basic thermodynamics books, and you'll be able to make this exchange from equation 4. I urge you to try these mathematical problems on your own. It's the only way you're going to learn and understand and remember yourself. Let's next look at some pressure gradients. And keep in mind these compressibility terms. They're going to come up later, and you'll have some homework problems. Look at pressure gradients and think about how pressure gradients might change the density in the flow. Remember, the equations are linked, as we'll talk about in the next class, through a system of partial differential equations, which relate pressures, densities, temperatures to, of course, the velocities. Closed but ideal gas law. For now, let's look at some physical observations of pressure gradients in the particular flows. First, we note that most flows, especially of aerospace interest, contain pressure gradients. That is, there's a change of pressure as we move through space and time. In this case, when I'm talking about pressure gradients, I'm thinking most in particular about how the pressure changes in space. It happens that many aerospace type flows are driven by pressure gradients. This happens to be the case for, say, rocket engines and wind tunnels. I'm sure you can think of other cases, if you take a moment, where you can think of a flow driven by a pressure gradient. Then think about flows, perhaps in nature in our lives, which are driven by, say, temperature. Now, strong gradients of pressure will, of course, create density changes, especially for a flow with high compressibility. It'll be much more susceptible to type of changes. And these density gradients will become larger and larger, and we'll have to account for them in our calculations. This, of course, is the central thought and thinking of the compressible flow theory of how we account for these density changes, which are so apparent and large in high-speed and very complicated flows. Now, this is not the case in an incompressible flow where there's pressure gradients, but the density is almost invariant or completely invariant. Mathematically, we could just say the density is a constant. Simplify our equations like you did in your fluid dynamics or introduction to aerodynamics type classes. So we could just say density is a constant and not worry about the changes of pressure with density, as we showed, of course, in equation 4 right here. If we say consider a portion on the right-hand side of the momentum equation, and you should have derived the momentum equations for fluids in your previous class, and we'll review them in the next class, you'll have one particular term on the right-hand side. This is what's used to drive the flow. You can think of it as type of an inhomogeneous or forcing terms in the equations of motion. Let's look at this form here. We have a negative symbol, which is obvious, and then we have our first instance in this class of a partial derivative. We say partial p partial x sub I. P is pressure. This symbol here in front of the p is the partial symbol. So this is a partial derivative with respect to the x sub I direction. If we're in 3 directions, I would be 1, 2, or 3 for the x, y, or z direction respectively. Then you see this curious character here. In the class website, I've uploaded notation for index notation. This is delta sub ij, where I and j are the indices of this particular term in the equations of motion. Here, I varies from 1 to 3, and so does j. When you see 2 i's, we sum them. For example, this term would be negative partial p partial x1 delta 1 j minus partial p partial x2 delta 2j minus partial p partial x3 delta 3j. Then we would set j to be the x, y, or z direction. So for example, in the x direction of the equations of motion, we have negative partial p partial x1 delta 1, 1 minus partial p partial x2 delta 2, 1 minus partial p partial x3 delta 3, 1. This delta sub ij is called the Kronecker delta function. It's 1 when I equals j and 0 otherwise. So therefore, in the x direction in a 3-dimensional system, we would have negative partial p partial xi times 1. Partial p partial y and partial p partial z would essentially be 0 because delta ij, the Kronecker delta function, would be 0. I suggest taking a few minutes to review the idea of Einstein or index notation in the class, because we will write some of our equations in this way, at least when we form the equations of motion. Through the rest of the class, we'll try and drop the index symbols, which were, of course, used by Albert Einstein predominantly. We call this Einstein notation or index notation to compactly write these equations. Nonetheless, this term is extremely important in the Eulerian or Navier-Stokes equations, which drives the flow and it connects to pressure gradient or density gradients. Look at it very carefully. Let's next look at Mach number. Let's define Mach number as I have shown in equation 6. M, we'll call M Mach number in this class, and we'll have subscripts on m to denote what kind, will be defined in general as the velocity of a gas divided by the velocity of a speed of sound. Mach number can be defined as any type of velocity, typically of a fluid, divided by some reference velocity. So we'll call the gas velocity generally a vector or value u. U is a velocity in this class, usually in the x direction, divided by the local speed of sound c. Now in this class, we will usually call speed of sound c, but some people prefer to use speed of sound a. Either way, we will concentrate on this definition. I try to usually use c. So when you see c, think speed of sound, and it's the local speed of sound. For example, in some flows, since density and temperature changes, temperature is very much related to speed of sound. In fact, the speed of sound goes as the temperature to the half power in ideal gases. So our Mach number goes as u over c, remember that. Here, u is the velocity and c or a, which we can use interchangeably, are the local speed of sound. Now if I add an infinity in the subscript to m, I call that the global Mach number. Say we have an aircraft flying through the atmosphere. Far away from the aircraft is the global Mach number. The global Mach number is also considered to be the aircraft Mach number, which would be the speed of the aircraft divided by the ambient speed of sound. That's the speed of sound very, very far away from the aircraft. Since the temperature around the aircraft changes in the fluid, which is an air or gas, we would expect the speed of sound to change. So the Mach number in regions around the vehicle will be changing because the temperature is changing, which changes the speed of sound. And of course, the velocity around the vehicle is changing. So the local Mach number around the vehicle changes. And we should discuss this more in our in-person sessions. Here, U is the velocity of the air in a stationary reference frame relative to the aircraft, very, very far from the vehicle. So U over C is the global Mach number. U infinity divided by C infinity equals M sub infinity. So when you say Mach number, it could be at a specific location at space and time. Global Mach number may not be changing unless the vehicle is accelerating or the temperature in the atmosphere is changing. So be aware of this difference between local and global Mach numbers, which we denote with these subscripts. Now, when we consider a flow to be compressible in aerospace engineering, as a rule of thumb, we see that the Mach number should be 0.3 or larger. So if we have a vehicle and it's flying at, say, Mach 0.1, we can get away, in engineering approximation at least, of course density is always changing in a gas, as saying Mach number, say 0.1, so we can ignore the compressibility effects. If Mach number is higher, say it's 0.5, then we would have to take into compressibility. And I should note that there's many, many exceptions, and in your homework sets I ask you to think of some exceptions to this rule of thumb. It's only a rule of thumb. This is not a rule of science. It's just engineering best practice. If your Mach number is greater than 0.3, you should absolutely start thinking about using a compressible framework or solver. There's also the idea of a turbulent Mach number, and we'll write that as M sub t. A turbulent Mach number might be viewed as a turbulent fluctuations divided by some reference speed of sound. So the fluctuations or the changes in the flow due to turbulence could be viewed as another Mach number, which we would call a turbulent Mach number. For example, we could have a global Mach number, or Mach number of the gas, being very, very small, like 0.01, and we might have a turbulent Mach number, which is very large. You should also recall the Reynolds number. If you don't, it's a good time to look back. We'll call the turbulent Reynolds number to be the same as the Reynolds number, but using like a turbulent reference velocity. And you should also be considered when you decide if a flow should be treated as a compressible flow or an incompressible flow. So you can see it's very possible that the global Mach number is very small, but the turbulent Mach number and the turbulent Reynolds number would be very, very large, and you would have to treat it as a compressible flow. If the flow is very low and you have low turbulence, low intensity turbulence, and a low speed flow, you can treat it as an incompressible flow, which was the subject usually of your previous classes. Now let's look at some flow regimes. This is fun. For subsonic flow, which is the first flow regime, we'll generally, these are rules of thumb and not hard cutoffs, as a global Mach number, say we have an aircraft flying lower than, say, Mach 0.8. This is just general. So if we have a Mach 0.4 global Mach number aircraft that's flying at Mach 0.4, then you can probably treat it as a subsonic flow, but it could be compressible. So you can have compressible subsonic and supersonic flows. And if we find the flow field solution of such a vehicle or flow field around one, we could say that the Mach number will be less than unity everywhere. That is, M is less than 1 everywhere. If we plot the streamlines of that flow, remember these are lines which are parallel essentially to the vector field, they will be smooth. That is, more specifically mathematically, that their first derivatives will be continuous. And I said just now, remember these flows can be compressible or incompressible. We'll look at examples of these soon. Let's look at a transonic flow next. A transonic flow might have Mach numbers in the range, rough range, between 0.8 and say 1. Where the Mach number everywhere is here. And it's also considered a subsonic flow. That is, we'll find that there's a subsonic M infinity. The global Mach number of, say, the device flying through the gas is less than 1. But there could be regions of the flow which are supersonic. That means M is greater than 1. And we could see that there's shock waves starting to form. So a transonic flow is usually an incoming subsonic flow which accelerates to be supersonic, and terminates and returns to a subsonic flow through weak shock waves. Now, if the Mach number increases more, then the shocks will move to the end of the vehicle and form bow shocks, like we showed in the introductory first class when we were looking at simple visualizations of Schlieren. You also find in a transonic flow, unlike a subsonic flow, that the streamlines are non-continuous in their first derivative, and on their discontinuities, they turn abruptly. They're non-continuous. The streamlines are non-continuous on particular flow phenomena, like a shock wave. And they're continuous everywhere else. This is just a general definition in transonic flow, and we'll talk more about mathematical rigorous definition near the end of the class. But for now, just try and get an idea of what the flow regimes are. Next, we have supersonic flow, where m is greater than 1. That's the global Mach number, m sub infinity, is greater than 1. So if we have a flight vehicle and it's flying at Mach 2, we would say m infinity equals 2, which is greater than 1, and therefore it's a supersonic flow. Here, the flow everywhere is greater than 1, and this is not a rigorous definition, because certainly a supersonic aircraft could be flying at, say, Mach 2 and have subsonic flow in regions around the aircraft. We'll just call this generally a supersonic flow regime. So remember, these are not hard cutoffs, they're just sort of rules of thumb to describe the types of flows, and we'll use them through this class. This is just the language of the field. Now, the flow, which in a supersonic flow, which makes it unique, is that everywhere in front of the flow will be unaware of the shock. And this is what we call a hyperbolic type system of equations, that information only travels in one direction. The flow will be unaware of shock waves in the flow if it's a supersonic flow and by the time it arrives. And you'll see this more in our mathematics through the class. If you don't completely understand that point for now, it's okay. Now, flow after the shock waves could be very much aware of the shock wave, because obviously you went through it, but it could also be subsonic or supersonic after a particular shock wave. And we'll look at these in the shock wave theory part of the class. There are tremendous mathematical difficulties when dealing with supersonic flow relative to subsonic flow because, of course, of these discontinuities in the solutions and the fact that they're shock waves. Compressible flow theory in this class will be simplified, and some students might think handling a supersonic flow is less complicated than subsonic flow, especially if it's incompressible. I assure you this is not the case, and unique flow phenomena happens in compressible flows that does not occur in the incompressible low-speed subsonic flow. So generally, supersonic flow will be that flow which has a global Mach number greater than 1 and has these general properties. But these are rules of thumb. This is not necessarily a rigorous math definition. Just learning language. Finally, when, say, a vehicle or a reentry vehicle in the atmosphere or some flow becomes a very, very high Mach number, say at least 5 or larger, that's just the community standard. If a Mach number is 5 or larger, we call that a hypersonic flow. So m infinity is greater than or equal to 5. So at these high speeds, eventually the flow becomes Mach number independent, and we'll look at Mach number independence later in the class. Remember, we can use Mach number, a non-dimensional number, to characterize flows and try and non-dimensionalize the solutions and collapse them and find similarities. These break down, and Mach number becomes useless at very high speed hypersonic flows. In hypersonic flows, if you have high enough Mach number in a particular vehicle shape, the gas may ionize and the gas may dissociate. That's like the space shuttle reentry you saw earlier. Plasma dynamics is also important in, say, in fusion reactor designs, for example, from ITAR, the Department of Energy. It's a very interesting field. We will not be looking at plasma dynamics in this class, but it's a wonderful research area to go in, especially if you're scientifically and mathematically minded. Plasma also occurs in both aerospace engineering and other fields. One thing you'll notice in a hypersonic field is the static temperature, pressure, and density increases by huge amounts across a shock wave. And we'll define these increases later. In any shock wave, you'll notice will be increasing the temperature T, the pressure P, and the density. All these scalar thermodynamic values increase immensely across shocks. And we'll find mathematical solutions of these in this class, and I think you'll find it quite elegant. One example of a hypersonic flow, which gives people great difficulty, of course, is the oxygen will liquefy from an air near Mach 5 in a wind tunnel. So if you're doing wind tunnel experiments at Mach 5 or greater, you can expect to have these types of difficult effects to deal with. The last flow regime I want to talk about today is the so-called hypervelocity flow. This is where you say have a Mach number of 20 or greater. So anywhere in 20, 25, and greater. The shape of the vehicle will also come into play here, as you'll see later near the end of the class, of what we call hypervelocity flow. But it has these general characteristics. One, that the flow will be rarefied. And we'll talk about what that means soon. That the continuum assumption breaks down. That means we can no longer treat with the fluid, in this case a plasma or gas, the standard mathematical assumptions. And we would say that the Navier-Stokes equations become invalid and that they could still be a good approximations. But in this class, we're assuming mostly continuum phenomena, non-rarefied flows, and we would have to have special tools, which are through the Boltzmann equation, which we'll introduce, and the Monte Carlo type methods to handle flows which are rarefied. A rarefied flow, of course, is a flow where we're dealing with particles which don't have a high density and are moving very fast. So we will talk about hypervelocity flow a tiny bit near the end through the original approach proposed of aerodynamics of Sir Isaac Newton. I think you'll find that very interesting. Now let's look at some examples of an airflow going through these different flow regimes. The first example here shown is a subsonic flow over an airfoil. So the airfoil, this solid body, is this outline with the diagonal lines going through it. And from left to right, we have streamlines. Now you'll notice in the subsonic definition, we said the streamlines are continuous through the flow field solution. So at some point B, we have a velocity vector, which is, of course, parallel to this particular streamline. We could draw these anywhere in the flow field if we wanted. You also see one particular streamline comes in from left to right and stagnates at the leading edge of the vehicle, the flight vehicle. In this case, it's an airfoil. So flow moves from left to right, the airfoil is stationary. It's not any different than sitting in an aircraft and looking out the side of the wing. The incoming velocity we'll call v sub infinity. So v sub infinity is the incoming velocity. It could be seen as the velocity of the aircraft or flight vehicle. And that's the velocity of the incoming airflow. M sub infinity is the global Mach number, and it's less than 0.8, for example, for the subsonic flow. Along all these streamlines, Mach number varies, and we say it's always less than 1. So everywhere in the flow field around the airfoil, the Mach number is less than 1. This is the stagnation point. We'll talk about that later in the class. This is where the flow comes in and it stagnates at, say, a leading edge. This is often one of the highest temperature points in the vehicle, which could be important at high speeds. So you'll see all the streamlines are continuous in this particular form. But also, remember through your analysis in your previous classes that along the streamline, Mach number actually changes. Why? Because, of course, it's compressible. We're incompressible here, but we'll say it's probably compressible because we're, I don't know, maybe Mach 0.8, M infinity. And the flow will accelerate. So the flow might be Mach 0.8 here, maybe it's 0.9 here, and it deaccelerates back behind the vehicle back to, say, Mach 0.8 eventually. Still subsonic. In transonic flow, something different happens. So this is the transonic flow regime, and this is very physically non-intuitive. So here we'll just say for this particular airfoil, the transonic regime goes from the range of Mach infinity, global Mach number 0.8 to 1. The flow goes from left to right, and it's the same airfoil. Now along the bottom, the Mach number never increases beyond 1. But what about this streamline? Let's say we're about Mach 0.85 here, and we accelerate, and we're still subsonic. And then something happens at this point on this dashed line. The Mach number goes transonic, which is m equals 1, and it accelerates to a supersonic speed. So at this location where my cursor is, that's a supersonic Mach number. And then we go through this thick line here, which is attached to the vehicle. That's the shock wave, which we saw pictures of in the previous class. And across the shock wave, we almost instantaneously, as we move from left to right, our little fluid element goes from Mach greater than 1 to less than 1 to subsonic speeds. And then we deaccelerate or accelerate a little bit, but then deaccelerate back to, say, Mach 0.85, the global Mach number. So as we change m infinity, the position of the shock wave will move around the vehicle, and it terminates so it can match, of course, the back pressure of the atmosphere and the flow. The dashed line here signifies the transonic condition itself, where m is exactly equal to 1. So that's a sonic condition or transonic condition. Everywhere on this dashed line, m equals to 1. So the flow out here comes along and accelerates, and it hits exactly Mach 1, and then it deaccelerates again. There's no shock wave. So out here, the flow is relatively undisturbed on the top part of the paper. Why doesn't a shock wave form on the bottom side of this particular airfoil? Well, it's the shape, and this airflow down here is never accelerated to a supersonic regime for a transonic shock wave to form. This is all physical observation, and we'll talk about the mathematics through the equations of motion to explain all this. Right now, I'm just trying to show flow regimes. So I'm sure you're wondering, and with a lot of questions like, what is a shock wave? Why does this happen? Well, we'll try and answer these questions in this class. Let's look at another transonic problem, and this time we'll define the global Mach number as from 1 to, say, 1.2. Here, since the incoming Mach number is greater than 1, and we do not have a pointed leading edge, the leading edge is bluff, a bow shock will form. So all the Mach number, say here, say m infinity is 1.1 is 1.1, hits the bow shock, and it goes to the shock wave, and immediately the Mach number becomes subsonic. And we'll prove this to you in this class. And if you go through a shock wave, your Mach number, for a normal shock at least, will become subsonic. The flow then accelerates around the body, it becomes supersonic again, and a trailing edge shock forms at the end of the vehicle. So this is a supersonic incoming flow, but it's considered transonic. Why? This has transonic features of a bow shock and trailing edge shock. And there's regions of the flow which are, of course, supersonic and subsonic. Let's now look at a supersonic flow through a wedge. So say I put like a little triangle element in my wind tunnel and turn it on and set my wind tunnel velocity to Mach 1.2. The airflow moves from left to right in Mach 1.2, and it hits the leading edge of the wedge. And an oblique shock wave forms, which is attached to the wedge. This is the left running shock because it goes to the left, and the right running shock because it goes to the right, as if I was looking downstream in the tunnel. This is the solid part of the vehicle. So the streamlines come in, and they hit the shock wave, and they turn instantly and go in another direction. So you see in this case, it's considered a supersonic flow entirely because everywhere the flow is supersonic, except of course in the boundary layers on the vehicle, which are not shown, or the device. So in this particular shock wave, we go through and the Mach number, that is the velocity divided by the speed of sound, remains larger than 1. Finally, we can take that same flow and increase the global Mach number to be greater than 5 for this particular wedge. You'll see there's not much difference between the supersonic and hypersonic flows except for the angles of the waves. One thing about hypersonic flows you'll notice is that usually the angles of these shock waves, which attach and form on the vehicle, have a very, very shallow angle relative to the vehicle itself. This is the vehicle turning angle, that's the angle of the wedge. With respect to the shock, that angle between, say, the center line in the initial velocity direction and the angle of the two walls, the wall and the shock, is very, very, very small. That's one physical phenomenon we see a lot in hypersonic flows to consider it hypersonic. But this is all qualitative, and we'll try and quantify these definitions later and put it on a more firm theoretical and mathematical basis. Let's return in this class to the so-called continuum assumption. Remember, we know that fluids are made of molecules through atomic theory, and we'll talk a little bit about the history of that in this class. And we'll see that the continuum assumption holds excellently in almost all cases as we previously discussed, except for hypervelocity flows, where the flow becomes rarefied and we have to handle it with like a Boltzmann equation and Monte Carlo type methods, which are statistical methods. The continuum assumption holds as long as the mean free path between the molecules is much less than the scales of the flow. For example, we'll estimate the scales of the flow as some distances and times. Those are scales, the length and time scales and velocity scales, for instance. And the mean free path, that's the average distance between the molecules, will be much smaller than the length scales of the flow. Then we can consider a continuum. And we'll do this mathematically in a few minutes. We would have to look at a whole new field called rarefied gas dynamics to handle situations where the mean free path length scales are on the same order or larger than the scales of the flow itself. Now, most aerospace flows that we'll consider are considered to be Newtonian. And here we'll define this relationship. This is unlike the compressibility equation which we introduced earlier in this class. Here we'll say tau is a shear stress. That's the shearing of the fluid, right? And a fluid deforms continuously under shear. And will be approximated as the viscosity times the derivative of u with y. This is a simple definition. This is not the full shear stress tensor. This is just for observation. Newtonian fluids, liquids, gases, or plasmas, are defined where the relationship is linear between the shear stress and the viscosity and, of course, the shearing of the fluid, du dy. This is a derivative of, say, u, the streamwise velocity, and the cross-stream direction y. Mu is a constant in this case, but it's often good to say there's a model for mu, which is viscosity, which goes as temperature. So it's like Sutherfield's law. Now, non-Newtonian fluids are much more difficult to handle. Can you think of some examples of non-Newtonian fluids? Two would be, say, honey or ketchup. So in our everyday lives, when we're dealing with honey or ketchup, we're dealing with non-Newtonian fluids. Now, almost all fluids we deal with have viscosity in reality. For example, a fluid with negligible velocity would be, say, liquid helium near absolute zero, just a couple Kelvin or less. And of course, physicists are able to supercool helium to this level and study it. And it essentially is a fluid when the viscous properties break down. And this relationship becomes meaningless. And the fluid can be defined and modeled with the Euler equations, which we'll look at later in this class. Now here's our first history figure. And in this class, we'll have many of these. And we brought up Kelvin. So usually where I find a famous name, I've already done Mach, but he'll come later, we'll show his picture and a little bit of history for fun. So he was born William Thomson, and he was the first Baron Kelvin. He lived from 1824 to 1907, and he was a Scot-Irish. He's a mathematician, physicist, engineer, and academic, and he was a president of the Royal Society. He was knighted in 1866 by Queen Victoria herself in Victorian England. His title, if you don't know, Kelvin itself, which is a unit of temperature, which we just introduced again, is named after the River Kelvin, and you can use Google Maps and look at it yourself if you wish. It flows by his lab at the University of Glasgow. Can you imagine being referred to Baron Kelvin, which is a nearby river? You can probably think of some examples right here in our state. He wrote over 650 articles and 70 patents. That's an amazing amount of productivity. He is widely known today because of his baronship of knowing absolute zero as approximately negative 270.15 degrees C. So you can see right here, this is about negative 273.15 degrees Celsius. When you refer to Kelvin or Rankine, which we'll also note later, you do not say it's a degree. Is of course it's just Kelvin. For example, we would say 300 Kelvin. We would never say 300 degrees Kelvin. Here's an oil painting of him near the end of his career in the late 1800s. It'd be fun if we all wore such academic robes on campus. He has an interesting quote, which I'll stop and share to take a break from the technical material. And he wrote, "In physical science, a first essential step in the direction of learning any subject is to find principles of numerical reckoning and practical methods for measuring some quality connected with it. I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely, in your thoughts, advanced the stage of science, whatever it might be. This is an actual photograph of Lord Kelvin. Of course, there's a statue which you can visit if you go to Glasgow in England. I put this quote here because you can see so far in this class I've only shown like rules of thumb and qualitative information of pictures of flows and talked about their general physics as we increase Mach number. Through this class, I'm going to try and follow Lord Kelvin's advice and show you a way to quantify this phenomenon into a science. It should be rather fun. Let's start with this quantification with the Knudsen number, who's named after another famous person. So we'll call Knudsen number Kn. Kn is a dimensionless ratio of the mean free path by the physical length scale. You can see I'm introducing this now because we've already talked about what's rarefied or not, and we have to decide if our problem is a rarefied flow or a continuum flow so we can apply the correct equations. I've already told you the outcome, the qualitative observation. Now, if Kn, this non-dimensional, is large, the flow will be considered to be rarefied. If it is small, then it will be continuum. So typically, Kn less than 10 will be considered a flow, which is a continuum. Now, in an atmosphere at standard temperature and pressure, that's STP, we'll find that mean free path will be 1 times 10 to the negative 8th meters. So lambda here is the mean free path, which I've just defined a few slides ago. L will be a physical length scale. What does that mean? That's like a length scale of the flow, like a turbulent length scale, for example. You'll have to know what these length scales are for particular flows to calculate the Knudsen number. I've given you an example problem in your homework to try it out yourself. Now, if we use, for Boltzmann gases, definitions for lambda and L, we can define the Knudsen number in a very quantitative way. It will be the Boltzmann constant Kb times the temperature divided by 2 to the half power times pi times d, which is a particle diameter, squared, times p naught, which is the pressure in the flow. In this case, it's total pressure, p naught. We'll talk about the difference between total and static pressure later, as I mentioned, times that length scale. This is how we define the Knudsen number. This is the general non-dimensional parameter definition. Here, Kb is the Boltzmann constant, which we'll talk about Boltzmann in a bit. It's 1.38064852 times 10 to the negative 23rd meters squared kilograms per second squared per Kelvin. Wow. And I'm sure you found this number in your chemistry classes. Here it comes back again. You might have never thought it would in the wonderful world of fluid dynamics and the idea of measuring a flow if it's rarefied or not. Let's look more at the Knudsen number. Let's try and relate it to Mach number so we don't have to worry about that scaling issue as much. Our goal is to relate Mach number and Reynolds number through the Knudsen number Kn. So we'll define a molecular average speed, c bar. So this is very much like a speed of sound, but now we're like as a parameter. But we're calling a molecular average speed c bar, and that'll go as square root of 8 times the Boltzmann constant times temperature divided by pi m, where m is the molecular mass. The mean free path can then be written through substitution of 15 and 16. The mean free path can then be written as lambda, as mu, which is viscosity, divided by the density, rho, times the square root of pi m over 2 Boltzmann constant times temperature. Now, if you look at equation 17 and you're keen, you can see that you can divide both sides by L and write Mach number as u over c, where u is the velocity and c is the speed of sound. But instead of speed of sound, we'll use the mean molecular average speed as c square root of gamma kBt over m. Gamma here is from thermodynamics. That's a ratio of specific heats at constant pressure and constant volume. Cp over Cv. Kb is Boltzmann, T is temperature, m is Mach number. We can simplify that as square root of gamma RT over m, and we'll see this relation later in class. And then we can also note that the ratio of m over Reynolds number we can rewrite So we've defined Reynolds number as rho u L over mu, and Mach number as u over c. Let's take those ratios and simplify and put in these terms from above into 18. And we'll get Mach number divided by Reynolds number of a flow will go as mu over rho L. Mu is the viscosity, rho is density, L is length scale, times the square root of m, which is molecular mass, divided by the ratio of specific heats gamma, times Boltzmann constant, K sub E, times the temperature T in Kelvin. And so now we have an interesting relation between these, but we're not done in our original goal. Now if we multiply the right-hand side of 18 by gamma pi over 2 to the half power, we'll obtain this form, which of course relates Knudsen number through equations 14 and 15. And we'll get mu over rho L square root of m over gamma kBt times square root of gamma pi over 2, which of course is a wonderful and pretty constant. We can then simplify this using our definition in equation 18 to equation 20, and we'll get Kn, the Knudsen number, goes as the Mach number divided by the Reynolds number times gamma pi over 2 to the half. And you can see that in these two terms, gamma pi over 2 to the half came down here. And this is really m over Reynolds number, as you saw from our previous equation. At this point, I strongly urge you to try this out for yourself, and you'll see the connection between Knudsen number, Mach number, and Reynolds number. But what does it mean? Remember, a high Knudsen number indicates that the flow is rarefied. So if we have a very, very low Reynolds number and we have a very, very high Mach number, our flow would be rarefied, which is very much the idea of a high-speed flight vehicle at, say, Mach 20. If we have a very large Reynolds number, a low Mach number, we have the happy case of having a continuum. It just happens that Kn, through this relation, for almost all practical problems we deal with, except a rarefied high-speed flow, will be on the order of 1, which is well in the regime of a continuum. And so almost everything we do in this class is applicable to all situations, except for the rare case. And you can use this wonderful non-dimensional equation, which relates three most important non-dimensional numbers for checking continuum, Mach number, and Reynolds number. Think about different cases in real life, say applications where m and Reynolds number changes, and try and calculate and think about how Knudsen number changes. And I think you'll agree with me, it's a wonderful tool to have. Now let's make some notes about what I just said regarding Knudsen number. For Kn, Knudsen number greater than 10, we should treat the flow as rarefied. Otherwise, we will treat the flow using statistical and continuum mechanics, which is the focus of our class. Now, thankfully, almost all flows that we are interested in as aerospace engineers are treatable as statistical and as a continuum, except for high altitude Mach number reentries. Also note that turbulence is by definition a continuum phenomena. So if Kn is greater than 10, you should not have to worry too much about turbulence phenomena. This isn't a wonderful thing because, of course, the turbulence problem is the most difficult part of the problem. So for high-speed rarefied flows, you don't have to worry about turbulence because it's a continuum phenomena. That's wonderful in itself and an advantage. So the harder problem is actually high Mach number and high Reynolds number, and low Kn, because it supports turbulence at high Mach number and turbulence, Reynolds number. Our final subject today, of course, will be the boundary layer flow. This is a picture from my good friend, Professor Mitchell in Australia. He has a wind tunnel where he can inject a dye and look at the turbulent boundary layer. Here's a single picture from his movies, and I'll try and show this movie in our in-person class. The black part is just the undisturbed fluid. The white part is the dye, and this line at the bottom represents the wall of the wind tunnel. You can see the flow is moving from left to right while his camera stays still. He takes pictures, and this is the actual relatively low turbulence intensity turbulent boundary layer. This is very, very close to the wall of the tunnel, and you can see it's very rich, all kinds of strange and interesting and aesthetically pleasing turbulent structures like eddies and vortices and tubes and roll-ups and all these things. I'll show a few movies of these so you get an idea what it is. This turbulent boundary layer only exists if it's attached to the wall, very, very close to the wall. Here's my own diagram of a turbulent boundary layer. Here we assume that there's a no-slip condition at the wall. So the streamwise direction is x, that's the direction that the flow predominantly moves, and the cross-stream direction is y, which is away from the wall. This is the wall itself here, and I've shown out here there's some velocity u infinity. There's a velocity profile as you move away from the wall, which is uy. This is what we call a boundary layer. A boundary layer can be laminar or turbulent. It's the fluid and its behavior very close to the wall. It must always be captured and predicted accurately to calculate the true drag of any type of device moving through a fluid. And there's whole classes and books on the ideas of boundary layer theory. It might be viewed in a simple definition as the thin layer of fluid very close to a solid boundary, that is, in this case, the wall. It was first proposed and put forward by Professor Ludwig Prandtl, who lived from 1875 to 1953. I believe it was in the early 1900s that he wrote a conference paper. He presented it on the idea of the boundary layer. Certainly he should have won a Nobel Prize for such a brilliant idea, but they cannot award to Nobel Prizes to people who've passed on by the time his idea came to fruition. Generally in this class, we will only look at the boundary layer problems of compressible flow a tiny bit, but I promise we'll return to it again and look at it in more detail. Let's note some differences that we observe between incompressible and compressible flows. In incompressible flows, generally the unknown variables which we need to solve for, but not always, but generally, are the pressure P and the vector U. In 3 dimensions, U has a vector with components U, V, and W. I've written U as bold here to indicate as a vector. Why is this? Because we only have to account for the continuity equation and the momentum equations. In a compressible flow, density varies. And you'll see it through the equations of motion which we develop in the upcoming classes. You'll see that we need to account for density, of course, because it's variation. When we make the incompressible assumption, we can say density is a constant, not changing, and we can get rid of it from the equations of motion. They simplify. So the compressible flow problem itself is more difficult because you have more variables. So usually there's 4 major unknowns if you count the vector as a single unknown in a compressible 3-dimensional flow. They're the pressure P, the velocity components U, V, and W, the temperature T, and of course density rho. So we would need a number of equations. We would need a continuity equation for conservation of mass, momentum equations for U, V, and W, it's a vector equation, an energy equation, say for pressure or temperature or energy, and a gas equation, like P equals rho RT, or a real gas equation, something more complicated, or any others, diatomic gas. And so in this case, we generally have many more unknowns, at least 4 if you're in a single dimension. So you need 4 equations, 4 unknowns if you're in one spatial dimension. I'm also not discussing the ideas of time and temporally varying flows. This is a mind for steady flows, which we'll talk more about in future classes. Now, we'll require that we formulate an energy equation and an equation of state, unlike the incompressible flow problems, which I just mentioned. This can become much more complicated for compressible flows. For example, if we have combustion or chemistry, we'll likely have tens to millions of additional equations per chemical species. For example, we'll need some sort of reaction rate equations, and there could be many different reactions in a typical, say, diesel cycle. In fact, the combustion community cannot even agree on how many additional chemical species and reactions happen in, say, a gasoline or diesel cycle. We're not including electromagnetics. For example, electromagnetic waves can affect and alter fluids, and that's a whole field called magnetohydrodynamics. That would require many more additional equations and terms, which are usually factored into the Maxwell equations. We are not dealing with nuclear effects. For example, if we're in a fusion system or fission system, we're not accounting for that, which requires additional equations. And we're not dealing with, in this particular class, the idea of multi-phase flow. That is where there's phase changes of, say, liquid to gas and vice versa, or plasmas within a one single flow, which requires additional complexities and additional equations. So in this class, I want you to be very clear about what we're focusing on. We're focusing on single phase flows without electromagnetics, without electrical effects, nuclear effects, and without chemistry or combustion. And the problem is so complicated, I think you'll appreciate the multiphysics that happens when we do need to account for those other effects. So we need to learn to walk before we can run, if you will. In this class, we looked at a number of flow regimes from subsonic, creeping, supersonic, transonic, hypersonic, and hypervelocity. We defined compressibility and talked about compressibility effects at different speeds. We discussed Knudsen number and derived the all-important Knudsen number relation, right, between Mach number and Reynolds number, and talked about their ranges of validity. We then talked about Mach number and defined it. The global Mach number, local Mach number, turbulent Mach number, and don't forget Reynolds number and turbulent Reynolds number. If you don't remember Reynolds number definitions, please visit your previous classes to see their derivation and importance. And if you want, we can talk about those one-on-one. Thank you very much for your time today. I'm Professor Steve Miller.